And next week we get to do antennas.
Who are?
Yeah.
You come to my house.
Well, I'd say we work on antennas.
Oh,
Okay, so there's a couple things they stuck in the front because they don't fit anywhere else. And we'll talk a little bit about waveforms and RMS again and PEP. And we talked about those. We could talk about them again. And how you measure, sine and square waves and other irregular ones, and how you do the RMS value of it. What the peak envelope power is. And we talk about analog to digital converters and, of course, the opposite, digital analog converters. Not much on that one. Some more about digital communications and Fourier analysis. We talked about that before.
yeah, that was when you were talking about that Smith chart thing.
No,
No?
no, not the Smith chart.
Okay.
Fourier converts time domain to frequency domain.
Oh,
So you see all the amplitude of the frequencies that are present in the waveform. So if it's like a square wave, you see all the odd harmonics. Okay, so RMS is essentially a way of calculating the average voltage of an AC waveform. And for a sine wave, it's simple. It's 0.707 or 1 over the square root of 2 times the peak value, or half of the peak to peak value. When you have a complex waveform, you can't use that formula. So if you want a multimeter or a digital meter that reads RMS, and they sell them, they cost more. It actually integrates the waveform by doing multiple samples. And basically you're figuring out the area under the curve to find out what the average is. Yes, it calculates. That's what they cost more.
They call it true RMS.
True RMS, yeah. The only other way to do it is measure the heat. Because by definition, it's the equivalent heat of a DC voltage across a known resistance. But I don't know any of them that work that way. Okay, this is just what I said. There's your formula. There's no question where you have to plug that in this time. You're frowning.
0.707 equals the square root of 1 squared over 2.
Yeah.
1 squared.
1 squared is what?
1.
Okay. The square root of 1 over 2 is 0.707.
1 squared. That's like 1 to the 49th power is still 1.
Well, I just plugged 1 in as the voltage peak to peak.
Oh,
for 1 volt.
I see what you did here.
Okay.
It's like that bad.
Just to confuse you. And there's our old waveform and the peak to peak and the peak voltage, and where 0.707 comes out, which is the essentially the average of that waveform. But you can't. The main thing that RMS does, because the square's in there, so you flip the polarity of the lower half of the waveform. Otherwise, it would be 0. It's got a positive and a negative. Another one. So what's the benefit of making voltage measurements with a true RMS calculating meter? Delta? So we talked a little bit about peak envelope power, And it's a lot of the definitions and things you see are confusing, but it's the highest instantaneous value of the signal. So when you got a modulated waveform, whatever that highest peak is the peak envelope power. You're looking at the shape of the envelope. And it's going to be affected by your speech characteristic. So if you kind of yell or have a very high voice, you get a peak on there, you're going to see a very high peak envelope power, where the average power might be much, much lower. Probably going to have a higher average for a male than you do for a female, because most of theirs is going to be on the higher end. So you may have more area under the curve, so you'd have a higher average.
Okay, so the female is gonna be higher.
Higher frequency voice most of the time. Not, I mean,
Okay.
there's some women that have low voices, but majority are higher pitch than a male voice. So when we look at the ratio of the peak envelope power versus the average for single sideband, they came up with this 2.5 to 1 ratio. It's kind of a typical thing. And that's 40% of the peak, which 2.5. The math is, But the key thing is to remember the 2.5 to 1. I didn't put it in red, but it's bold, because guess what? There's a question. So what determines the peak envelope power to average power ratio of a single sideband phone signal? We have alpha, we have a Bravo, 2 Bravos. Change your mind, huh?
Yeah.
Speech characteristic is the shape of the waveform. What's the approximate ratio of PEP to average power in an unprocessed single sideband?
The number you gave us. Oh.
Now, notice they said unprocessed, which means no speech compression or equalization, which would change the waveform. Because what the speech compressor does is essentially shift the frequencies higher. You get more energy in the higher frequencies. Okay, enough of that stuff. Analog to digital conversion. Essentially all the modern radios are at least partially SDR and have digital signal processing systems in it, at least for audio, or the IF. If it's a direct conversion, it has a lot more, doing the equivalent of what a super heterodyne would be doing with mixers and filters. So the basis is, for those, is using an analog to digital converter to get it directly into digital form. And all the A to D does is take samples of the analog waveform at a fixed, usually at a fixed sample rate. And that's what gets processed. So the number of output bits for the A to D converter is going to determine what resolution you can have. We talked about that last week. So if I had a 1 volt reference level on the A to D, and it was a 10-bit converter, then my resolution would be approximately a millivolt. Because there's 10,024 steps. And if it was an 8-bit one, which you could use for audio, I guess, it'd just be 256. One of the things in determining a good A to D is how much total harmonic distortion it generates. Because it's not a perfect device, it's not perfectly linear, so you're going to get some harmonic distortion. And one of the measures is they look at the sum of all of the harmonics compared to the fundamental frequency. So they're looking at that ratio.
How do they determine all those harmonics?
You have to look at it with something that does an FFT, like a spectrum analyzer. And there's, I thought I had it in there. There's a chart I have that kind of shows the harmonic distortion over a wide frequency range for one, a typical A to D. But all you really need is to know what resolution you would get with 8 bits. So which of the question? Which of the following is a measure of the quality of an A to D converter? Powerful. They call that other chart where they look at the ratio as the goodness factor.
Could you back up 2 slides? Please?
2?
Oh,
One more?
okay.
That one?
Oh, what's with the C here divided by?
256 divided by the gain of the input amplifier.
Oh,
Well, that's a bogus answer.
yeah.
Some answers are just totally made up.
Okay. Again, I saw 256.
8 multiplied by the gain is, if the gain was 10, it's 80. What's that got to do with this?
Yeah. This is called I got you. Okay.
But so your choices are really 8 or 256.
So pick the right 256.
Okay, so in the case of an SDR radio, particularly if it's like a direct conversion, you need a very high speed analog to digital converter. If you're looking at, even the HF band, if you were doing it at VHF, you really are looking at some high speed A to D. One of the techniques that they use is called a flash or direct conversion, as opposed to, and we talked about a successive approximation last week, which is more accurate. It's much, much slower. It's good for audio. I don't think there's any way you could use it at really high frequencies if you had very high resolution. So in a flash, there's a kind of a block diagram of what a 2-bit flash converter looks like. So you've got, since it's 2 bits, there's 4 states. So you're looking at 4 different reference voltages, and you're comparing the input signal to those 4 different those taps on there are going to give you a different reference voltage. So depending on what your input is, these comparators are going to give you a 1 or a 0 output. And then you go through the logic that converts that into one of 4 states, either 0, 0, 0, 1, 1, 0, or 1, 1. In one that's like 24 bits, it's pretty complicated logic. That's why they're rather expensive.
Well, it's not complicated, it's just,
Well, a lot of it.
yeah.
Yeah, but it expands out. So why are direct or flash conversion A to D converters used for a software-defined radio? Because the only delay is the delay time through those gates. Whereas successive approximation, if you had a 20-bit, then you got to go through 20 steps. And we'll talk a little bit about the successive approximation A to D. They're more accurate, but they're very slow. They're much cheaper. It doesn't take all those gates. I mean, it's fairly simple configuration. And essentially it works by stepping through the number of bits, and you're looking at whether it's less than or greater than. So you add a 1 or a 0 to the accumulator, and that's driving a digital analog converter. So every time you step through one, you're changing the reference voltage that you're comparing against. And once you get through all the steps, then they should be essentially equal. So whatever digital pattern you wind up with that's generating that reference voltage that's the same as the input voltage is going to be your digital output. There's a little block diagram of it. I'm not sure what the EOC represents except for the output. I couldn't figure out what that EOC stands for.
Input count.
Maybe. That's close to what I thought maybe it was. But it's run by the clock and you're just stepping through, and each time you step through, you compare that pattern the analog version of that pattern back to the comparator. See whether it's greater or less than. So then you go to the next lower bit. So you kind of start at the highest bit and you work your way down. Which of the following is a type of analog to digital conversion? Okay. The other thing that they do, which is a little hard to wrap your mind around it, is they use a technique called dithering, where they actually inject noise into the input signal to the A to D. And it makes it more accurate. So they'll have a noise generator set to approximately 1/2 of the least significant bit of the converter. So if your converter was 1 millivolt minimum, then they'd inject about 1/2 of a millivolt noise. And what that's going to do is going to cause the inputs to oscillate around 1/2 a least significant bit. So if your input voltage is, say, not quite up to the 1-bit level, You add that noise, sometimes it's above, sometimes it's below. The percentage of time that it's either above or below, okay, is going to average out and give you approximately a half a least significant bit accuracy or additional accuracy. Because now you're kind of doing an analog of proportionally where it is in the range. It's still a little hard. Well, you're adding it to your input wave. So you're changing your input signal by that much. If it was a solid signal and it was just slightly below the comparator, you'd never know how far below it is. You just know that it's between this level and this level. When you add dithering, it's a way of finding out proportionally where it is in the range.
Because the noise is the known value that it can.
That's what they tell me.
Yeah.
It's what the internet says.
That's why it's certified.
What is dither with respect to analog to digital converters? They also use digital analog converters on the other end, because you come in analog, you manipulate it in the digital world, and then you convert it back to analog so you can hear it. Because the output of a digital analog converter is a stair-stepped waveform, you actually have to low pass filter that or integrate it because you want the envelope. So that's what the low pass filter does. Low pass filter is essentially an integrator. What's the purpose of a low pass filter used at the output of a digital to analog converter?
Oh,
Charlie. Yeah, spurious sampling artifacts are the stair steps. And those stair steps are going to generate harmonics also. Fourier transform, like I said, is used to convert a signal from the time domain to the frequency domain. So in the time domain, you're taking samples of the amplitude of a signal at different points in time. In frequency domain, you're looking at the amplitude of signals at different frequencies. So if you had a pure sine wave and you convert it, you do an FFT, all you're going to see is a peak at whatever that fundamental frequency is. If there's any distortion in it, then you're going to see some additional peaks that are harmonics or subharmonics that are part of that waveform, if it's not a pure sine wave. Let's see. And it basically shows you the frequency content of whatever the waveform is. In most waveforms, you're going to have, you'll see multiple peaks out there of varying amplitudes. Like in the case, and I think it's probably the next chart, of the square wave, you're going to see the fundamental at a high amplitude, and then you're going to see the odd harmonics at decreasing amplitudes. The even harmonics are going to be zero. And there's a picture. So if we have a square wave, you've got a fundamental, which is this waveform. And over here is the FFT. So you see the amplitude of the fundamental is that, I guess these are hertz. Could be a megahertz, whatever, but it's 1. Okay, the second harmonic is 0. Third harmonic is up here at what, about 0.5. And the fifth is like 0.3, and they kind of go down exponentially, never get to 0. Because a perfect square wave would have an infinite number of odd harmonics. If you've got a triangle wave, then you get a much different, where you get the fundamental again, same. But now I'm getting odd harmonics that are adding and subtracting. They're plus and minus, very low level. And that's what this is trying to represent. The red line is your fundamental, and then this dotted red line are these little odd harmonics, and the result is this green one. And of course, once again, the more harmonics you've got, the closer that's going to be to this wave here. Of the sawtooth. Yeah, I was talking about the wrong one. This was just for the triangle wave. The sawtooth has all positive, but it's odd and even, as opposed to just being odd. So what technique shows that a square wave is made up of sine and its odd harmonics? Good old Mr. Fourier. Which of the following describes a signal in the time domain? Okay, so we learned about RMS again, and average versus peak envelope power, particularly for a single sideband and that 2.5 to 1 ratio. That you need a low pass filter for a D to A. Total harmonic distortion is one of the quality measures for an analog to digital converter. The number of bits determines the number of levels and the resolution. Flash converters are high speed, successive approximations or slow speed. Dithering will give you greater accuracy up to half of a least significant bit addition. So they claim. And FFTs is time to frequency domain conversions. And an inverse FFT goes the other way, frequency to time. Any questions on that one?